So we're going to get into chapter number 27. And in chapter number 27, we're going to be talking about the right current circuit. So let me kind of give you guys like an overview of what we're going to be talking about. So let me share my other screen here. So let me provide an overview. Chapter number 27. So let's write chapter number 26 here, and then let's write chapter number 27 here. Or I should say chapter number 20. Now, if you remember in chapter number 25, we looked at this type of problem here where you can have, for example, let's say a capacitor here. This, all of this is connected to some supply. And then, for example, we can say that this is my delta V. So this is delta V. Let's say, for example, let's just say that this is C1, this is C2, and this is C3. All right. So if you remember, we said that we can calculate the equivalent capacitance. Then we can also calculate, for example, what is the energy in the equivalent capacitance. Then I can also calculate what is the energy in each of the capacitors, E1. All right, so there is a question from online about the test. So it says that, did we all fail the test? No, the answer is no. So I'm still looking at the test. I've not graded the test yet. So as I said, I was a little bit busy this week, but hopefully I'm going to get that graded by today. So I'll let you guys know once I have your grades on day 2. So do you see that in chapter number 25, we're looking at, so this is a circuit. But this circuit only has a capacitor. So capacitor plus body. Now, what we're going to do in chapter number 27 is that we're going to look at a circuit that looks like this. So basically the same type of thing, but instead of capacitors, we're going to have resistors. So for example, I can say, let this be R1, let this be R2, and let this be R3, and let this be delta V. And so we can do basically the same thing. For example, we can calculate the equivalent resistance. We can calculate the energy in the equivalent resistance. And we can also calculate the energy given to each resistor. We can do basically the same. So I want you to see the connection between the two. So in chapter number 25, we're looking at a simple circuit that only has a body and a capacitor. Now in chapter number 27, we're going to look at a circuit that has a, so again, this is my body here. Then this would be my resistors. Then finally, so once we're done with that, we're going to wrap this chapter up by looking at a circuit that looks like this. So notice that this will have a capacitor in it and a resistor in it. So this is plus and this is minus. So this is called an RC circuit. Now, do you see why this is called an RC circuit? Why? Because it contains a resistor and a capacitor. All right, so this is just an overview. So let me go back and share let's get into the PowerPoint. So the very first thing that I want to define is this quantity here. It's called the electromotive force. And so let's look at this simple circuit. So this is my resistor. This is my body here. And this is my switch. Now delta V is the voltage. So delta V is called the and I is my current. Now, so by definition, the electromotive force is defined such that is given by this equation here. So this symbol here is called, so this is called, this symbol is called epsilon. And we're going to use it to represent the electromotive force. So let's try to understand what this electromotive force is. So the electromotive force, so all of this is my body. So the point is that a body has an internal resistance. Now this internal resistance, what it does is that it kind of reduces the voltage. Now, to make this to be a little bit understandable, let's look at one example here. So let me share the screen. So let me share. So let me look at this example here. So let's call this the electromotive force. So electromotive force example. So let's assume that we have a body that looks like this. So all of this is so the body always comes with some internal resistance. So let's say we have the resistance, the external resistance is 10 ohms. So all of this is my body. So notice that the body has some internal resistance that is given by, so the internal resistance is always given by lowercase r, which is, let's call this 1. And this body has an EMF, we call this 12 volt. So when this body is connected to this resistor, let's calculate how much amount of current is going to flow in the circuit. Now, if I want to calculate the current, what I need to do is that I need to calculate R total. And when I calculate R total, I'm going to add the external resistance to the internal resistance, which in this case is 10 plus 1, which is 11 ohms. And I know that R total, so R total is equals to my voltage. So in this case, my voltage is 12 over current. So solving this, you get your current for R total. So this would be 12 divided by 11. And so this would give me 1.0, let's just say 1.09. Now, if this is my current, so if this is the current, then I can calculate, so what is the voltage across the resistor? It's just going to be I times R, which is given by 1.0 minus 10. Now, again, so this is the difference. So do you see that so the resistor is getting only 10.9. It's not getting all the 12 volt. And the reason is because there is some amount of energy that is lost in this internal resistance here. Now, what if the internal resistance was equal to 0? If the internal resistance was equal to 0, then my R total would just be equal to R, which is 10. Then in this case, my current would just be equal to E over R, which would just be equal to 12 over 10. This would give me 1.2 amps. And so in this case, if you calculate the voltage across the resistor, This will be 1.2 times 10